We left off our discussion on initial stages of VSEPR theory with the question of how do those things happen? How does it happen that we can get those shapes from our atomic orbitals? That's our topic for today. So just quick review of what we already know. We know about VSEPR theory, at least we know the beginnings of it. We know our basic shapes. We know that those electron groups are going to end up as far away from each other as possible, which makes sense in our head, but would not make sense if we were to attach it to what we know about atomic theory right now, which is quantum theory, where those electrons have wave-like properties, and then they go into these orbitals that have no fixed location, no fixed shape. We just talked about probabilities. So this is how we've been representing an s orbital. It's spherical. It looks flat here, it looks like a circle, but it's actually a sphere, three-dimensional shapes. And once we go into our second sub-energy level, so L equals 1, so M sub L is -1, 0, and +1, that means we've got p orbitals, three different orientations with the same amount of energy. If I have a third sub-energy level, and yes, I can have more than that as well, but I'm going to leave it at 3, then I have more orientations that are possible. Now I want to back up just a little bit and take a look at those 3 p orbitals, because those are the ones that I think make the most sense. I'm going to have one orbital that is going perfectly up and down. So it's going along the, what is that, the z-axis right there in the middle, and then I've got one that's going left and right along the y-axis, and one that's coming out toward you and back in toward me on the other axis. But I've got 3 orbitals. Each orbital has 2 lobes, but each one of those represents one orbital, but they are 90 degrees away from each other. And then don't even get me started on the d orbitals, but there are 5 of them, so we have 5 different orientations, because we have 5 different possible orientations. Now if I were to represent orbitals using a box, and I'm going to pick the third energy level because it has those 3 sub-energy levels, I would draw one box for the s orbital, I would draw 3 boxes for the 3 p orbitals with the different orientations, the -1, 0, and 1 on my m sub L, and I would draw 5 for the other ones. Now if I were to start populating those boxes with electrons, and I'm going to kind of do that in a moment, but if those orbitals were what I was going to be using for bonding, and if those orbitals as they exist in the previous slide there, if those orbitals exist in the way that they are also for lone pairs, I'm not going to get VSEPR shapes, so I'm going to have to do some modifications. We cannot have shapes like linear, because think about this. If this is how I was going to get a linear shape, and by the way, that arrangement would not give me linear, but if you were thinking, well, okay, something like that, 2 bonding groups, 2 lone pairs, that would give me a linear arrangement. It would not, because those p orbitals need to be 90 degrees away from each other. So even though I could say, yes, here's how they bond, it's not how they end up existing, because I need it to be a different shape. And again, that linear shape would not come from that orbital arrangement, but that's not the point. Okay, so what might happen? The theory is that we're going to end up with hybrid orbitals, or hybridization. And what that means is I combine orbitals from different sub-energy levels into this new kind of orbital that I use for bonding. Not for running around doing atom things, but when bonds form. And they're going to mix characteristics, and then they're mix energies. We're not going to worry too much about the energy, or we're not going to get down to the details of, oh, how much energy do they have. Not even really worried too much about their characteristics. We're going to look at it briefly, but it's not going to be a big focus for us. And they are only used in the formation of molecules. Like I said, atomic orbitals are for atoms, and these hybrid orbitals are for molecules. Now, if you were to go Google molecular orbitals, recommend you don't, but if you did, you're going to find that this goes really far, much deeper than what we're going to. By all means, knock yourself out. So we're going to talk about molecular orbitals in a very simple, I think a very simple, but a very initial or starting point way. Then also we've got this notion of VSEPR theory, which is those orbitals pushing away from each other as far as possible. And again, that should be okay, because an orbital is just where am I likely to find an electron. If I'm repelling those electrons, they're going to go somewhere else where there's less repulsion. So where do we start? We're going to start with an sp orbitals, or I shouldn't say with a sp orbital. We're going to start with sp orbitals, plural, because I'm going to use s orbital and p orbital. That's multiple orbitals. So if I were to take a system where I have 2 electrons in the s orbital and no electrons in the p orbitals, but those p orbitals are allowed, they're available. What's going to happen is I'm going to form a bond. I'm going to promote one electron from the s up into the p. So now I've populated two orbitals with one electron each. Now I can form bonds, single electron to single electron. But in order to form the molecule, the molecular orbital, I'm going to combine, I'm going to hybridize those orbitals into a new kind of orbital called sp. Excellent name, right? I took an s orbital and one of the p orbitals, and I get an sp hybrid orbital. I get started with two orbitals, I finish with two orbitals. Started with two atomic orbitals, I finish with two hybrid molecular orbitals. And those other two p orbitals, well, they were never really there. They're just allowed. They were never being used. They're still not. I'm going to keep them written in there because it'll avoid confusion or something. So now I've got these orbitals called sp, two of them. One from the s, one from the p. Now, if I were to combine those and hybridize those, I'm going to combine their characteristics. So you'll notice that these purple orbitals, the new ones, they have two lobes, like the p orbital, but then one side is much, much larger. It's much more spherical, bigger, bubblier, kind of like the s orbital. We're not going to worry too much about that, like the degree to which they have that. It's still an orbital where I'm likely to find an electron. But now I'm much more likely to find an electron in the larger lobe, much less likely to find the electron in the smaller lobe. And the larger lobe is where I'm likely to find the electron because that's where the bond with the other atom is. I'm not really drawing that part in. Now, if I were to combine those together into the same nucleus or onto the same nucleus, it starts to look like that. Please do not confuse that with a pure p orbital. This is two separate orbitals. They just happen to be as far away from each other as possible. They are linear. Now, on those orbitals, there should be, so I'm not going to draw it because it gets messy, but there should be a bonded group on each of those bigger lobes. Okay, moving on, hopefully a little bit quicker this time. sp2, well, guess what? Same thing. I'm going to take one electron from my full s orbital. I'm going to promote it up into one of the empty p orbitals that was not being used but was still possible. That gives me electrons in three separate orbitals, so I've got three single electrons I can form bonds to. I'm going to hybridize those. I'm going to combine those three orbitals, not combine them into one, but combine their characteristics and then hybridize them into three new orbitals. Now, please don't look at this as the reverse of something from the top, because they are not the same. They look suspiciously similar, but they are not the same because these first three boxes are hybrid orbitals. They're called sp2. Again, fantastic name. One from the s, two from the p. Gives me one from the s, two from the p, three orbitals going in, three hybrid orbitals coming out. That lone p orbital is still just sitting there doing its own thing. It's actually not there at all because a p orbital is not a thing unless it has an electron in it. What would that look like? Well, if I took those three orbitals and combined them and hybridized them, I would end up with three molecular orbitals that would share characteristics of each. Putting those as far away from each other as possible and combine them onto a single nucleus, I would have my sp2, I would have my trigonal planar Vesper shape. So you'll see, hopefully, we're connecting these things together. What about sp3? What do you think is going to happen there? Well, similar kind of thing. I'm going to promote and I'm going to hybridize, so now I've got four single electrons in separate orbitals, and then I'm going to hybridize those into a new kind of orbital called sp3. All three p orbitals, one s, four orbitals going in, four orbitals coming out, and that's going to start here, finish here, and then combine together to make my sp3, my tetrahedral Vesper shape. Now I want to point out that the hybridization does not require a promotion. It can start with much more full orbitals to start with, and I still need to get those orbitals as far away from each other as possible. So far I've not had lone pair electrons, but lone pair electrons are still going to be a possibility. Ha! Yeah, you see what I did there? So what if I did have lone pairs of electrons? Well, I would still hybridize because I want the orbitals to be as far away from each other as possible. I don't have to promote anything if I don't need to, if I don't need that extra bonding capacity. Well, same thing, I can combine them. I don't have any new or any more electrons that are singled up so that they can form bonds, but I still have those things as far away from each other as possible, and they're still sp3 orbitals. Okay? So something like water that has 2 lone pairs on my central atom and 2 bonding pairs, sp3 hybridized. And it would look like that. Got to look your way there. Now, I can go larger. You remember when we started doing Lewis diagrams, some people really struggled with this notion that I was breaking the octet rule. How can I break the octet rule? Like this. So if I take an atom that has d orbitals available to it, I can start doing the same thing. I'm going to do the whole promote. I can't really draw the arrow so well. Promote, hybridize, combine them together, make now 5 orbitals that are sp3d. And that's going to give me my Vesper shape that is a trigonal planar, and of course anything based on trigonal, it's not trigonal planars, my apologies, trigonal bipyramidal. Anything based on that is going to come from this hybridization. And likewise, doing the same thing, if I have to promote and hybridize enough for 6 bonding pairs, bonding locations, then I'm going to do that. Now I've got 6 hybrid orbitals giving me my octahedral and everything based on that, and that is sp3d2. Whew, getting complicated. All single bonds and lone pairs are going to use hybrid orbitals. That's where, so count up the number of bonding groups, count up the number of hybrid orbitals, and you'll notice I said it a little bit different. I didn't say single bonds. Count up the number of bonding groups, count up the number of lone pairs. That is going to be the number of hybrid orbitals you need, and then which one do you use to get that many. We still have to deal with multiple bonds, and that'll be another time. Okay, but at this point we now can take our central atom that we can do from a Lewis diagram, we can figure out what hybridization it has, and then we're going to add more pieces to this some other time. Talk to you then.